All right, welcome to module number 28. Recall that we're discussing machine learning, and in particular, we looked at this in decision theory in the previous module, where there are different error metrics, and the learning means that we want some model or some parameters to minimize the error, or perhaps we should say to optimize some utility function, and small error would be favorable utility. And we saw how different types of error, absolute error, squared error, error to the power of 4, can accent different types of goals. Absolute error would be very robust to outliers, or an outlier would not have a significant impact on the output of the algorithm, the learning. Whereas if you're taking the error to some higher power, really we would be dominated by the outliers. There would be very little weight given to the smaller errors, resulting in a situation where you're tailoring the learning to minimize outliers. And maybe that's a good thing. Maybe if you're extremely confident that outliers are actual true issues with the measurements, maybe the information is located in the outliers. Okay. On the other hand, there's much to be said for robustness, and in many applications, it might be better to not, instead of doing the classical traditional L2, to do something which is somewhat in between the L2 and the L1. But bottom line, we want to optimize something. And now, in many cases, we have the data X, and we have the corresponding measurements, functions Y, but sometimes we don't. And this brings us to clustering. Now, I'm presenting clustering partly in the context of project number 4 in 2020, and I'm recording these modules with an eye toward future versions of the course. And I'd just like to mention, it could be that this is, if you're watching this in a future year, it could be that there's no project 4 or there's another project entirely. But I'm just saying that in 2020, there's a project 4 which is relying on clustering. So we have data. Again, we have X, we don't have Y. And this could be called by some people unsupervised learning. Supervised would mean that we're supervised by Y. Unsupervised would mean that we're trying to learn structure in X without Y. And we want to group data into clusters that seem related. So this illustration may be helpful. We have 2 different panels. The panel to the left, we have 2-dimensional data, x1 and x2. So the data appears as dots in a 2D plane. And we see that this area over here, there seems to be a lot of data, a dense, packed range of dots. And the other areas seem to be less packed. And we want to separate this data into clusters. So now on the right panel, we have 3 colors. We have red, green, and blue. If some of you may have problems differentiating the colors, these are plots from the book, so not my colors. Especially the green and the red can become complicated for many people. So the dense cluster of dots on the lower right-hand side is now in red, and then the upper range is in green, and then to the left we have blue. Now the notion here is as follows. We want similarity between different clusters. So what do we mean by similarity? Within each cluster, we'd like the dots to be sort of packed together. And the typical algorithmic approach is iterative. We move points between clusters, and then for each of these clusters, having defined a certain configuration of points of clusters per point, we recalculate the cluster centers. Because the cluster center, recall what we were saying for decision theory, is conditioned on the points that have been mapped to a certain cluster. The center, the average, minimizes the squared error. Now, again, you might be targeting something which is a bit different from squared error, in which case you may not want the actual centers. You may want something a bit different. But for now, let's assume squared error, and that'll be reasonable in many applications. So here's the k-means algorithm, which you're going to be studying in the project. In the project, you're going to have an image. You'll be partitioning it into patches. For example, a 4x4 patch of pixels. And now that 4 by 4 patch of pixels is a 16-dimensional space, whereas on the previous slide I illustrated a 2-dimensional space. And you're going to want clusters for that 16-dimensional space. And these clusters, each of them is going to be associated with a representation level. Think of this as quantizing a 16-dimensional space. And this is how you're going to quantize a 4 by 4 patch of pixels into perhaps 16 different clusters. 16 different clusters, 16 different possible 4 by 4 patches in your dictionary can be selected using 4 bits. 2 to the power of 4 is 16, the number of clusters. And because of that, to represent these 16 bits, we would need 4 bits, or rather 16 pixels are represented with 4 bits. And that would be an example where the number of bits per pixel is 4 bits per 16 pixels, which is a 1/4 bit per pixel. Now, modern image compression algorithms can give very nice quality at that type of coding rate, namely a 1/4 bit per pixel. And if you were to try to do this, probably your performance will not be quite as good, because the approach that I'm describing is not that sophisticated. Now, what if instead of 16 clusters, you do, let's say, 64 clusters? So 64 is 2 to the power of 6. And now you're going to have a dictionary of 2 to the power of 6 4 by 4 patches. You're going to have your image for each of the patches in the image. So the image may have, let's say, 1,000,000 pixels, and you're partitioning 1,000,000 pixels into 1,000,000 divided by 16 parts, so something like 64,000 parts approximately. And for each of those 64,000 patches, you're mapping it to the closest patch among the 64 in the dictionary, and then you can describe that using 6 bits. So 6 bits for 16 pixels. Now we're going to have a rate of, well, 6 divided by 16 is 3 divided by 8, which is 0.375. So instead of a 1/4 bit per pixel earlier, now we're at 0.375. You may get somewhat better perceptual quality. So what you're going to see in this project is that more patches, a larger dictionary, give you better quality. And additionally, you're going to see that a 2 by 2 patch is not going to be as efficient as a 4 by 4 patch, meaning that for a 4 by 4 dictionary, which will be encoding 4 by 4 patches, for the same coding rate as for 2 by 2 patches, you're gonna get a somewhat better visual quality with a 4 by 4, and that's because in a 4 by 4 patch there's more 2-dimensional structure, and this 2-dimensional structure is going to be picked up by your dictionary. Okay, so how do we do that? We're using the k-means algorithm for the clustering. So we initialize k-cluster centers. You just select k points in the training data. That's it. Then you iterate as follows. First of all, you associate each training data with the nearest cluster center. So let's start putting numbers on these, okay? So suppose 1,000,000 pixels, and we're looking at 2 by 2 patches, which is 4 pixels. Okay. Now, if we have 4 pixels per patch, that means number of patches is 250,000. And for each patch, we'll map it to the nearest one in our dictionary. And the clustering means determining an appropriate dictionary. Okay, so now let's look at these iterative steps. Again, there are 2 to the power of b for bits, patches in our dictionary. And to keep it simple, suppose we're doing 2 by 2 patches, 4 pixels. So let's say 4 bits per 4 pixels is going to be 1 bit per pixel. So b equals 4 bits per 4 pixel patch means 1 bit per pixel. Now with modern image compression techniques, 1 bit per pixel is on the higher side, and you should get outstanding quality. And this approach is not going to be quite so outstanding, so you'll probably get okay quality. But let me just suggest that you'll go through the work, and then you'll see it for yourselves. And I think that for this type of project, seeing things visually is going to be part of your learning experience. There's the machine learning, which is what we're talking about, but also your learning experience will be seeing things and seeing how for, let's say, 3x3 patches or 4x4 patches, we get better results. All right, so with 4 bits per patch, we have 16 patches in the dictionary, and we initialize the dictionary by choosing 16 randomly. So we have, to reiterate, 250,000 patches in the actual image. We're, excuse me, we're selecting 16 of them randomly. But then, having chosen 16 randomly, those are cluster centers. Those 16 are cluster centers for each of the 250K patches in the image mapped to the nearest one. So now we're going to have each of the 250,000 patches is going to be associated with one of 16 patches in our dictionary. Okay, these are going to be cluster centers. And the group of image patches that maps to one element in the dictionary is going to be called a cluster. Okay, so we performed this mapping. We associated each of the 250,000 to the nearest patch. And then there's another step. We recompute the cluster centers. So to minimize, so given the cluster, so now this is, you can think of this as slightly similar to the EM algorithm. So you're associating, and then you're re-optimizing. You're re-optimizing the dictionary, the representation patch in the dictionary that corresponds to that cluster. So given the cluster, the associated patches, we optimize error to the cluster center. Or maybe we shouldn't call it center. Center implies average to the dictionary element. Now, suppose that we want to minimize squared L2, squared error. This would, as we saw last time in decision theory, this will lead to conditioned on being in cluster number 2, cluster number 7, etc., conditional expectation. Average over the locations of the patches in the cluster, which really means compute the cluster center. Compute average or center cluster. And when I say cluster, I mean the patches in that cluster. Now, if we want to minimize another type of error, so for example, imagine that you reach a conclusion that the human eye is in smooth areas of the image is very sensitive to error, and around edges of the image is less sensitive. So maybe because of that, it would make sense in smooth areas of the image to require a greater fidelity, and around edges, when the image is jagged, maybe a reduced fidelity. So if we have some other type of error, and I just described the rationale for some other type of error, it wouldn't necessarily be squared error anymore, can be minimized in another style. And just as an example, see the decision theory model. All right, So we're going to iterate over these. This is, again, sort of like EM. We are populating the clusters from the dictionary, 16 places, 16 typical patches in the dictionary. And then, having populated the clusters, we're recalculating that dictionary element, okay? Iterating, hopefully until it converges. There may be problems with convergence. You know, this may get pretty good performance in a few dozen iterations, or it could be many thousands of iterations. So to get this to work well is somewhat of an art, and you'll be looking into this in part during the project. So part of the problem is that this algorithm is sensitive to initialization. Based on how you selected the initial k points in the training data, you could get stuck in a local minimum. Another problem, well, what is k? We've discussed this before. So this is called the k-means algorithm because for each of the k clusters, each of the cluster center is going to be the mean of the data in that cluster. But again, there are other variations along this theme, just as we discussed a different type of error that we may want to be optimizing. All right, so let's move to the next slide and a bit more about k-means. So we're going to map the data point, the datum, xn, index number n, to a cluster C of n. For each n, C of n is going to map us to some k, and k will be an index for a representational level, again, a dictionary element. So we have 16 possible k's in our example. We have 250,000 possible n's, and k is going to be a function of n, k of n, which is also denoted by C of n, cluster of n. Primarily, many applications, we're going to want to minimize the squared error between the xn's and the corresponding representation levels, the rk's. And the overall distance is a summation over all the n's. But what's a summation between xn and the corresponding rk? So here the notation is perhaps slightly problematic because we want in xn, we want element number p in a p-dimensional cluster. Let's say we're using a 2x2 cluster, so p is equal to 4. And in rk is a vector, a 2x2 patch, we want element number p. So perhaps a more consistent notation would be xnp and rkp. So, you know, I'm not really sure. You can, as long as your notation is reasonable, that's, you know, we'll be fine. So we are summing over the squared error per dimension. And another way to write this is the squared L2 norm between the vector xn, which is a p-dimensional patch, and the vector rk, which is a p-dimensional patch. Again, it's a vector in our dictionary of cluster centers. Now we want rk to minimize for all the n's, for all the data points that map to k. We want to minimize the error between xn and r subscript k. To do so, as I said before, for L2, for square type of error, we select the cluster center. We just take the average. And the sum square errors for the mapping are as follows. The error of an overall clustering technique is a summation over all capital N points of the squared error, the squared L2 norm between xn, datum number n, and the representation level, which is indexed by k of n. Now, recall that we have capital K different clusters, and for each of these clusters, we have a range of points that is mapped to that cluster, and we have a summation over the squared L2 terms of the different xn's minus the single rk within this summation. So ideally, a globally optimal solution is you fix capital K, you want the mapping C of n to be such that the cluster center for each of these mappings minimizes the overall function error of C. And this is why I was saying earlier, there may be a local minimum, there may be a certain partition into clusters such that after calculating the cluster center, any swap between 2 points between clusters is going to increase error of C. But it could be that that's a local minimum and there's an entirely quite different overall clustering scheme, which is better. So that's why I was saying earlier that initialization is can be a sensitive matter in these algorithms. So that's it for this module, and hopefully my comments will help you work through project number 4.